Hi everyone, this is Kalyan Kumar and welcome once again to Chemistry Universe. This is the part 8 of the 13-part series of General Organic Chemistry, and in this one we are going to talk about the stability of various carbanions. If you remember, in the last video we discussed what the reactive intermediates were. We talked about carbanion, carbocation, free radical, carbene, nitrene. In this one we are going to look at the stability of carbanion. So let's get on with it. So remember, the stability of a carbanion increases with -m, -h and -I effects, while it decreases with +m, +h and +I effects. So basically what we are trying to say is that the stability of an anion, not just a carbanion, for that matter any anion, the stability will increase by withdrawing effects. Effects that withdraw electron from that atom, disperse the charge, decrease the negative charge on that atom, which is what -m, -I and -h effects do. And anything that releases electrons, that increases the negative intensity on that particular atom, would definitely decrease the stability of the anion. So let's take a few examples. Ion 1, ion 2, third, and this is the fourth. Now if you notice here, this basically is CH3, CH2 negative, whereas this guy is CH negative, CH3, CH3. This is C negative and 3 CH3s, and this is simply CH3 negative. So what kind of effects do you think are happening here? And which do you think is more stable and which do you think is least stable? Try to figure this out. Now the first one has one methyl group's +I. Remember, methyl group is +I. Even though the electrons of this bond will be actually moving like this, but remember, the inductive effect is not a relative effect, it's an absolute effect based on hydrogen as reference. So this is going to push the electrons towards this. So it has one methyl's +I, this has two methyl +I, this has three methyl +I, whereas there is no +I effect. And what do you think plus effects do, releasing effects do? They decrease the stability of the anion. So the order should be 4, 1, 2, 3. So let's look at one more example. As you can see, now I want you to pause the video now. These are the 4 molecules you need to compare. And pause the video, figure out the stability on your own, then play the video back. Now if you look at the first one, here you have one structure which is this itself, and then it has some resonating structures. This negative will go here and the double bond will go here. So you get the second structure with minus here, then the minus comes here and this will move here and the minus moves here. So how many resonating structures do we have? We have 3 resonating structures. So the first one has 3 resonating structures. If you look at the second one structure is anyway this, and the second is this. There are 2 atoms on which the negative is being spread. So there are 2 resonating structures here. Now this one also has 2 resonating structures similar to the second one, but the problem only is that this one has a +I effect also working. So this one has 2 RS and 1 methyl +I. Now look at the fourth one. This is interesting because here the negative one structure is this itself. This is the second one. This is the third one. But if you look at NO2, let me draw NO2 like this. So if you draw NO2, you will notice one is that it has a -I of its own, strong -I because of the positive on N, and the second is when the negative is here, it is conjugated with this double bond O, So you will have one more resonating structure, more than what you saw in the case of 1. And that too, the one in which the negative is going to O, whereas in all the others, the negative is actually on carbon. So fourth structure has 4 RS and 1 nitro minus I, and that too in the fourth RS, you have the negative being spread on O. So obviously the order should be 4 more than 1 because it has got more resonating structures, and out of 2 and 3, 2 should be more stable because 3 has plus I also. So the order should be 4, 1, 2, 3. Let's try one more. Now pH, remember, is benzene ring. This is also 2 benzene rings and this is 1 benzene ring. I think pretty sure you must have understood what all this signifies, because if you have a benzene ring, remember, the negative will delocalize in the benzene ring. You will get several structures here. So in fact, in each benzene, the negative charge further gets delocalized on 3 more atoms per benzene ring. So a lot of delocalization in 1 because it has got 3 benzene rings, than in 2, than in 3, and the order therefore should be 1 more than 2 more than 3. Now try this one. Now on the face of it, it would look as if the second one is more stable because it's got 3 benzene rings and a lot of resonating structures, whereas in the first one, the resonating structures are only 5 because the negative will spread on 5 atoms if you draw all the resonating structures. But the only thing is that 1 is also aromatic. So it's got 5 resonating structures, but it's aromatic, whereas 2 has only 10 resonating structures, and the aromaticity of benzene has got nothing to do with the stability of the carbon ion. So in 1, it is the conjugation, it is the resonance of the negative charge, the lone pair, that makes it aromatic in the first place. So 1 is more than 2. So let's look at one more. Allylic carbanion and benzylic carbanion. Now 1 has how many resonating structures? It's got 2, and 2 has 4 structures. 1 in which the negative is right on this carbon, and 3 more when they are in benzene ring. So obviously more resonating structures, 2 more than 1. Let's try some more. Let's compare allylic with something similar to allylic. The only difference here is there is a double bond O instead of double bond carbon, and I think you must have guessed it right, that obviously there are 2 resonating structures in both, but in 2 the negative is actually on O, and that makes it 2 more than 1. Let's compare these 3. What do you think? Now remember, there is no resonance or anything, but remember the carbon's hybridization. This fellow is sp3, whereas this is sp2 and this is sp, and we know that negative charge is more stable on the more electronegative element. Here the element being same, the hybridizations are different. So sp carbon is more electronegative than sp2, which is more electronegative than sp3. So obviously sp3 carbon, sp2 carbon, sp carbon, I think we can get the way 3 to 1. Alright, try this one. So what do you think? Now obviously when you compare 2 and 1, it's pretty simple. 2 should be more than 1 because 2 has 3 fluorines which are withdrawing by minus I. When you compare 2 and 3, it might look that 2 is more than 3 because F is more electronegative than Cl, will withdraw more, shows minus I effect greater. But in CCl3 negative, there's one more thing that is working up, and that is there is a back bonding with the d orbitals of chlorine, because remember chlorine is in third period, it has got d orbitals and the lone pair is conjugated with them, lone pair single bond empty orbital, and there will be resonance taking place. But this is not as good as a normal resonance with the p orbital is, which is why we call it back bonding or d orbital resonance. But at least it is happening here. It is not happening in F though, and therefore in 1 you have no I or M effect, in 2 you have minus I effect, whereas in 3 you have minus I as well as back bonding. So 3 is more than 2 more than 1. Try this. And whenever you get these questions, pause the video. Now you should pause the video and try to find out the stability on your own and then check. If you look at the first one, the negative charge is on this carbon. Eventually it will come here, then it will come here, and then it will come here, always going into the alternate atoms. But here you have N double bond O, O negative. There is further resonance. So you have 4 resonating structures, 4 atoms on which the negative charge is spread, including O, which is not happening in the case of meta, but it is happening in the case of para. But in one, you also have a minus I effect of NO2 itself. So this shows both minus I and minus M. Here NO2 does not show minus M at all, shows a very less amount of minus I. In 3 there is hardly any minus I, but there is sufficient amount of minus M, just like in 1. And we know that mesomeric effect dominates. So the stability order should be 1, where all are withdrawing effects, then 3, then 2. Looking at the next one, try this. Now obviously you can see here that O is withdrawing minus I. Here there is sulfur which will have empty d orbitals. Here both sulfurs have empty d orbitals. So I think that's pretty simple. This is the last set of molecules. So figure out the stability. I think this is pretty simple because you got 2 resonating structures in one in which the minus goes to 1O. In second one, you have conjugation on both sides happening, and here you have conjugation on all the 3 O's. So obviously more resonating structure in 3 than in 2 than in 1. So 2 resonating structures, 1 on carbon, 1 on O. 3, 1 on carbon, 2 on O, and 4, 1 on carbon, 3 on O, and that makes 3 more than 2 more than 1. So that is the end of this video. I hope this video helped you in understanding how to predict the stability of carbanions. Please understand that prediction can only happen to a certain extent. Everything that we do in chemistry is explaining the facts that are known to us. And in doing so, we create some rules. But remember, nature being nature itself is not going to follow our rules every time. So there will be situations where one thing dominates, another situation where another thing dominates. And the more experience you have in trying to predict the stability of various types of carbanions, the better you will become at predicting if something unknown is given to you. So with that, let's wrap this video. This is Kalyan Kumar signing off. Have a great day. Goodbye and thank you for watching this.